Okay, so here's where we were last time. We were talking about integrals on surfaces. So we wrote down a Riemann sum that for which we developed this notation. The idea being that, look, if you have a surface in space, I mean, it's a two-dimensional thing. It's in a three-dimensional world, so it's not exactly a double integral. It's not exactly a triple integral. What are we going to do with this? Well, we're going to take the same chop it up, add it up strategy, and to little pieces of area on the surface, we're going to, for whatever reason, multiply by some sort of a integrand, some sort of a density, right? Some sort of a stuff per unit area that we're going to multiply by area, okay? And then add up over the entire surface is kind of how you can think about the notation. And then we asked the question, how do you compute these things, right? And that turned out to be not that big a deal. The point is you can write down a formula for what a piece of area is if you pull back through a parameterization. That's the big idea, is you got to pull back through a parameterization. View your surface as being the image of something more reasonable, like this, a two-dimensional region in a two-dimensional space. It's dimensionally sort of where it should be, in some sense. And so doing that pullback, you get a double integral in the UV plane. And here's the formula. So the stretching factor, recall, we talked about that last time. The stretching factor is this. That's the magnitude of capital N. Don't forget that capital N itself is XU cross XV. You just have to remember that formula. By the way, it's important for more than just doing surface integrals. These kind of surface integrals. It's important for other things that we're going to see later on. Okay, so it's a good formula to make sure you definitely have memorized. Okay, so that's where we finished. We did this example as well. A couple more examples that we did. So picking up from there, it turns out that there's an extra formula that I think you should know. This is a special case. The special case of if the surface you're looking for is a graph, specifically a rectangular graph. So it's z is a function of x and y, in other words. So graph, in the sense that you've solved for one of the variables in terms of the others. Rectangular graph in the sense that these are rectangular coordinates. Right? You can also talk about spherical graphs, and that's a separate thing. So these rectangular graphs, a lot of surfaces are. Right? Very often that's how we find ourselves looking at surfaces, is as graphs. So how does it work in that special case? Working it out, streamlining it for that special case can be really efficient. So here's the thing. If you have a graph, we've talked about this already, there's this really convenient construction called the graph parameterization, that I call the graph parameterization, that you get by that trick. Make x equal to u, y equal to v, and z equal to whatever it has to equal based on the fact that you've already decided what x and y are. Right? So if you use the graph parameterization, write that down. Here's what your XU will be every time. Here's what your XV will be every time. Here's what the cross product of that is going to be every time. Right? And here's what the magnitude of that cross product is every time. So the point is, instead of going through this, take partial derivatives, do a cross product, compute the magnitude. Instead of doing that whole process, you can just memorize this formula. Right? It's very convenient. Now, again, this is a special case. This only works if not only your surface is a rectangular graph, but you are viewing it as a rectangular graph. You're viewing it with the graph parameterization. Okay? But in that special case, nice to have all the details already worked out. So feel free to memorize this formula. And there's a typo in here. Oh, yeah, right. So sorry about that. ds is stretching factor times du dv. Here's your stretching factor. Right, and I just forgot to transcribe the delta in here. Sorry about that. There should be a delta right there. So if you have these notes printed out, please correct accordingly. Okay. So anyway, suit yourself. I think this is a good formula to use sometimes. Now, I want to emphasize this is not an alternative to the original formula. The original formula is much more general. This formula here only works in the case of a rectangular graph. Lots of surfaces are not rectangular graphs. Spheres, for example, again, as I often like to say, the world's full of circles and the world's full of spheres, right? So not graphs. This formula will not work for those cases, right? So this works only sometimes. So it's a good supplement to know. It is not an alternative instead of. Okay. All right. So that finishes up that section from last time. So we are now moving on to chapter 15. You've all heard the rumors. Chapter 15 is there's some really wonderful things that happen in chapter 15. This is math. This is some of my favorite material to talk about. But it is geometrically challenging. There's a lot of kinds of pictures that you have to kind of get accustomed to and learn about. There's various algebraic constructions that we're going to create. We're going to talk about new kinds of integrals that we haven't talked about before, right? And it's going to turn out that these various constructions, these various kinds of integrals relate to each other in unexpected and extremely powerful ways. And more that I can't. I'm getting too ahead of myself here. But so there's lots of wonderful things that happen, but it is challenging. So we're going to go through this kind of slowly. Right? I've been deliberately going a little faster paced than maybe a lot of instructors do in the first part of this course, so that we will have more time to really dwell on all there is that's going on in chapter 15. Yeah. Let's see. So the cutoff date for the exam is Wednesday. So the cutoff date is Friday. So yeah, whatever we finish by the end of Friday is fair game. And I'll send as usual. I'll send an email about that on Friday. Yeah. Okay. So all right. The first thing that we're going to talk about is a new kind of object. This is something that y'all might have seen conceivably, but probably not. Something called a vector field. So this is, you might say, the main sort of object of study in chapter 15 is vector fields. Well, more to the point, things that you can do with vector fields. So first thing we have to talk about is what is a vector field. And here's the big idea. A vector field just associates to every point in space, it associates a vector in that space. Right, so an easy example. This is a vector field in R2. So notice we're in R2 because there's an x-axis and a y-axis. Right? This is not in three dimensions in any sense. That is a vector field in R2 because for every point, for every location, keep in mind points are locations. Right? We're associating to that point a vector, and I'm associating the vector at that point by drawing it at that point, with its tail at that point. Okay, so for every point, here's several different points. Right? There is a corresponding vector that I represent by drawing arrows. Now notice for different points, they're different vectors. Right? So that's the idea. For every point there is an associated vector, and they don't necessarily have to have anything to do with each other. Okay. Likewise, now here's a vector field in R3, and this associates to every point in R3. And now look, this is a point in R3 because there's three coordinates. Right? And at that point, I'm going to associate a vector. And just to help you see what that vector is intended to look like in this case, and it's just an example I made up, nothing really important about this example, but I'm going to draw these little guide framework indicating the x, y, and z coordinates. So that arrow, I'm intending for you to view that as sort of going into the page and sort of down and to the right, if you will. Okay. All right, so for every point, there's an associated vector. So notice you can think of that as a function, right? So keep in mind the idea is that for every point, whether it's a point in R2, point in R3, whatever, for every point, you can think of that point as the input to this function, and the output from this function is, well, what is the vector that you associate at that point? You give me a point, there's an associated vector. Input, output. Yeah, anyway, so we use this as a means of writing down the vector fields, but then, of course, you also need to draw pictures of the vector fields. So just to see how this works as functions, here's an example of a vector field written as a function. F of x comma y equals, that formula. So what does this mean? I'm going to try to illustrate how we're representing the vector field I'm intending here with this formula by noticing that if I were to plug in the point 1, 2, there it is, 1, 2, right? Plug in, do the algebra, see what you get. Well, what comes out, this associated vector, is 0, 2, and I can draw 0, 2 right there. All right, now this does not represent the entire vector field. Of course, the entire vector field is, all the vectors that you associate to all the points that you get by plugging in any possible x and y into this function. So the whole vector field is, it'd be something more along these lines, right? But here I just want to point out specifically how the formula is representing the vector, how the formula tells us for a given point how we get an associated vector. Now let's talk about these pictures just a little bit. There's something incomplete about this picture. Let's look at the R2 picture. Notice that on this picture, while I've told you what the associated vector is there, and I've told you what the associated vector is there, and there, and there, I have not told you what the associated vector is at that little point. Right? Why didn't I draw that? Maybe I should have, right? I mean, if I've got to have an associated vector for every point, why didn't I draw it there? Well, you can probably tell what's about to happen here, right? If I were to draw an arrow at every point, then the picture would just be a solid black, right? It becomes useless, right? So that's kind of one of the unfortunate, it's kind of like with level sets. You remember we were talking about level sets? You can't draw every level set. Your picture becomes just a solid, it's like you spilled ink on the page. I mean, it's just a solid black, uninterpretable mess. Likewise here, you typically draw a representative sample of arrows and just sort of accept that you're not going to have a perfect picture of your vector field. You're going to see some of the vectors, and the rest you kind of have to infer. Okay. All right. Another thing to say about these pictures, they're not graphs. This is not the graph of a vector field, right? We have a specific formula for graphs, right? If I were looking at a vector field in 2 dimensions, like one of these here, a graph, 2 input variables describing the point, 2 output variables describing the associated vector. That's a grand total of 4 variables. This is not a 4-dimensional picture. It's not a graph. These are also not level sets. This is not the image. We're not parameterizing the vector field here. Right? So this is yet another, I think this is arguably the 5th separate, distinct kind of picture that we've drawn in this class to represent certain kinds of functions. Right? So for vector fields, this is the kind of picture we draw. Make sure to interpret it appropriately. Please do not make the mistake of thinking that the slope there is somehow the derivative of the vector field. That's not. That's for graphs. This is not a graph. Yeah? Everybody on board? All right. Okay. Here's a couple of easy examples of vector fields. Here, the associated vector 2, 1 is always the same vector, so it's easy to draw this field. It's always 2, 1. Sweet. What about this one? F of xy equals xy. Okay, so this says for every point, the associated vector, hey, look at that. The associated vector also x, y. The associated vector at that point is the same as the position vector of that point. Here's the position vector of that point. So the associated vector that I draw here, same vector as that position vector. Yeah.
Is the input and output all the same number of dimensions?
Yes. Yeah, it does have to be. So a vector field in Rn, always n-dimensional points, always n-dimensional vectors. Absolutely. Yeah, great question. Once you make this realization, f of xy equals xy has this feature that the field vector is always the same as the position vector, then it's not hard to draw a bunch of example vectors, and you sort of get a vibe of what this thing looks like. Okay, here's one. What does this one look like? F of xy equals negative yx. So here the position vector and the field vector are not the same, but they do have something in common. They have the same magnitude. They're always perpendicular to each other. The field vector is always perpendicular to the position vector. And if you combine those, it's not hard to persuade yourself that the picture ends up looking like this. So any given point, like say that one, the field vector is perpendicular but with the same magnitude as the position vector of course being that, and so you get something like that. Everybody on board? How did I know it was going counterclockwise? I plugged in an example. Right? You plug in x and y both equal to 1, like I have drawn here. If x and y are both 1, then the field vector is negative 1, 1, as opposed to 1, negative 1, which would be going clockwise. Right? So anyway, plug in an example. You can see which way it goes. Okay. Now, how do you, in general, draw pictures of vector fields? It's different with every one. There's no single magic formula. But roughly the idea is, look for geometric good fortune, such as in this case, and then, draw a few sample vectors, and you can sort of start to get the idea. Okay. Here's a vector field that we've actually done work with in the past. We just didn't think of it that way. Gradient fields. Now, y'all remember gradients, but you don't remember gradient fields because we've never talked about them as fields, but I claim that they were, and we just didn't notice at the time, right? We just didn't think of it that way. So here's a very familiar idea. Real valued function on Rn, chapter 13. We did a lot of stuff with this. We know how to take the gradient, right? A bunch of partial derivatives, make vector valued partial derivative. The gradient is a vector in Rn. We already knew that. Notice then that what we have, whether we chose to view it that way or not, for every point in Rn, there is an associated, you can compute the gradient of the function at that point, and you can call that the associated vector. This is a vector field. Right? So it's just that at the time, we were only viewing gradients sort of one point at a time. Now I'm just making the observation that you can view the formula for the gradient all points sort of at the same time as being a vector field. So here's an example. This function, right? Here's the graph of that function. It is a graph. Right? Here is the gradient, right? Again, boring. Chapter 13, we already know how to take partial derivatives. That's easy. We just thought of it one point at a time. But now notice that you could view this as a field. And I'll leave it for y'all to think through. This vector field looks kind of like that. The idea is that the field vector is always double the position vector. So it's another one of these outward, sort of, radially outward looking vector fields. Now, how is this relatable to anything that we saw back in chapter 13? Well, let's draw them kind of together. Keep in mind that the graph includes the domain only as part of the graph, right? So the graph lives in this combination space that has both input and output variables on it. But anyway, that's right, what you might say how the domain looks on the graph picture. The gradient field lives entirely within the domain. So combining those observations, here's what the gradient field looks like on the graph picture, right? So these arrows, these outward pointing arrows like that, right? This is what they look like on that graph picture. And notice this recovers this old idea that we had of the gradient always points uphill, right? So for example, let's take that point. Get this stuff out of the way. At that point in the domain on the graph, here's the associated point on the graph. And if I were to ask, at that point on the paraboloid, which way is uphill? Well, it's that way. Right? The gradient points uphill. So you can view this all sort of at the same time, though, and make the observation that this vector field, always outward and with greater magnitudes the further you get away from the origin, that tells you how uphill works on this paraboloid. If you're inside the paraboloid, if you're an ant trying to climb out of this bowl, you're always going to want to walk away from the z-axis, away from the origin in the domain, in other words, and the further you go, the steeper it gets. So, anyway, yeah, highly relatable. Okay. All right, how are we doing? I'm going real fast here. Is everybody on board? Any questions? Feel free. Everybody's happy. Okay. Okay, so what does this have to do with physical applications? Y'all are engineers, largely, anyway. What do these have to do with the physical world? It turns out a tremendous amount. There are lots and lots of real physical things that are most conveniently represented with vector fields. So an easy one to talk about is forces, thus the name force field, which sounds like a sci-fi thing, but it's not, right? It's a vector field representing forces. So you've probably heard about this thing called the gravitational field, right? The sun creates a gravitational field, right? Well, okay, the reason they call it a field is because it is an example of a vector field. It is a vector field. It's a vector field representing gravitational force, thus the name gravitational field. So anyway, so how does that work? Well, here's the formula for the gravitational field. This probably doesn't look exactly familiar, but it looks probably, I hope, vaguely familiar. I'm sure didn't see it written in this form, but you have seen in a high school physics class probably this formula for force of gravity as a scalar, right? And it's negative g m1 m2 over d squared. So I hope that looks familiar. And if not, if you haven't had a high school physics course before, this is the formula for the force of gravity. So there you go. Okay. So how are these relatable? Well, the difference is, as a vector field, this includes a direction, whereas representing a scalar, that does not include a direction. That's just a quantity. So what's the deal with the differences? First of all, let's start with y the cube down here. That looks like a typo, right? That's a cube. This one's a square. That doesn't seem right. So let me rewrite this a little bit. Let me rewrite. I'll use blue here. This formula here is negative g m over magnitude of x squared. Hey, that's not fair. You can't just do that. So let me put that over here, x over magnitude of x. Now I'm legal again, right? And notice what we have here. We have inverse square for distance, just like we're supposed to, right? And it's just that this quantity, this magnitude of gravity is being multiplied by what you'll now recognize as a unit vector. Right? So in the cube, one of those factors in the cube is part of what makes the vector portion of this actually a unit vector, so you can interpret this as magnitude times direction. Right? So even though you see a cube in the denominator, this is actually an inverse square magnitude. Everybody on board? Okay, yeah.
Will we need to memorize that formula?
Yeah, I think it's a good one to know. Yeah, let's go ahead and do that. And we're going to do much more with gravitational fields later on. So you don't need to memorize it right this second, but later on, it's definitely something I think you should know. Yeah. All right. Okay. Other question that we need to address about this formula is what's the deal with this second mass? Where did that go? Did we just sort of throw that away? Right? What's going on there? Okay, well, the high school formula that you see here for the force of gravity is telling you what the actual force is between two actual masses. If you give me two masses, then there's a force of them pulling together, right? Okay. What the vector field formula is telling you is not quite that. It's telling you, look, let's just look at the one mass. that one mass is creating, we would like to think of it anyway, as creating this thing called a gravitational field. And then when I then decide I'm interested in a second mass, then I'll take the gravitational field and I will then subsequently multiply by that mass to get the actual force. Right? So you might say, in other words, that this isn't really force. This, wrong color. That's the other. Let me do this with green. Here we go. This is not really force. This is acceleration. Right? This is the thing that when you multiply by the second mass will give you the gravitational force. Okay, so it would sound weird, though, to call this a gravitational acceleration field. It's just easier to call it gravitational field. Okay. All right, so little physics aside there. Okay, so punchline, though, is for every point, right, wherever you might happen to be at any given point, x, right, there is an associated... Let me go ahead and get all this junk out of the way. There is an associated vector. This formula gives you, for every point, a corresponding vector. That is a vector field. Yeah, everybody happy? Not hard to persuade yourself. Just kind of think about, what happens if you put in different kinds of points. The further the point is away from the origin. By the way, this mass is thought of as being at the origin, of course. The further you are away from where the mass is, the smaller this vector field is going to be. So the weaker the gravitational pull is out there. And again, highly relatable. Everybody on board? Okay. All right. Electric fields. Now, it's more likely, I think, that you haven't seen electric fields. Anyway, here's a formula for it. Electric fields, you'll notice, by the way, it's hard not to notice, they look a lot like gravitational fields, just mathematically. Now, of course, physically, it's very, very different, right? Electric charges, it's different. It's a different thing, a different concept. But mathematically, look at what we've got. We've got this radial, we've got this x vector. We're dividing by magnitude of x cubed to make this inverse square radial. And then, constants, whatever, physicist's problem, right? So from a mathematical point of view, constant times x over magnitude of x cubed is what both of these are. Mathematically, they look a lot alike. So here's a neat fact then. It turns out that because these vector fields, these physically very different vector fields, mathematically look a lot alike, it turns out that the mathematical conclusions that you can draw about gravitational fields and electric fields end up being really, really similar. And we're going to see that play out later on in this. Yeah. Mm-hmm.
Will we have to memorize the value of the constant?
No. Just know what the letters are. Yeah. No. I couldn't tell you what the values are for most of these constants. Yeah. Right. Yeah. Yeah. Mm-hmm.
So for most of the physics formulas that appear even before this, we should memorize the formula.
Some of them yes, some of them no. The really basic ones like F equals ma, I think came up at some point, right? Sure, we should know that one. Kind of a big deal, right? But obscure formula, I can't remember off the top of my head every physics formula that we've talked about. Maybe some you might not. But anyway, let's talk about that some other time. Yeah. These I think you should eventually know because they are pretty fundamental. But we'll talk about. You don't need to memorize them now. That'll be a later thing. Okay. All right. So, what do vector fields represent physically? Well, they represent forces. That's our first example. This is not our only example. This is just one example of something that vector fields represent physically. There's another really important one, and that is flows of fluids. I think this one's arguably easier to relate to, right? So how air is flowing in this room, for example, right? There's several different sources of airflow in this room. There's AC is on for some reason. And people are opening the door, I'm talking, people are moving around. There's a certain amount of airflow in this room for various reasons, right? How would we represent, if I wanted to mathematically represent the flow of this fluid of air in the room, pretty reasonable thing to do would be at any given point in the room, we say, okay, at that point, what's the velocity of the air? What direction is the air going and how fast is it going in that direction? Right? Well, we would represent that velocity, of course, with a vector. Now, at every point, there is an associated vector. That's a vector field. That makes sense? This is a really extremely natural physical example of something that's very well represented by a vector field. So flows of fluids, and I enumerated a few examples of flows of fluid. How air is moving through the room, sure. How water is moves around in the ocean, right? Any point, there's always a current. Same deal. How does pollution move around? Well, pollution might be moving around, and contaminants, likewise, whatever, might be moving around in a way that's not necessarily exactly what the flow of the water is. Right? Things like this. There are two-dimensional examples. How do animals migrate? Well, they're mostly stuck on planet Earth. Right? I mean, we don't need to keep track of how every time they jump up, right? So it's the vertical movements that we want to keep track of. So animal migrations you can think of as being a two-dimensional fluid flow represented by a vector field, right? Etc. Okay. All right. But I'm just as a cultural note, we're not going to do anything with this really in this class, but sometimes the vector field that you use to represent the flow of a fluid is not just velocity, sometimes it's velocity times density, and there's a perfectly natural and reasonable reason for that. If you're curious, come talk to me. I'll be happy to explain it. It's no big deal, but I just wanted to mention it's not always exactly velocity, sometimes velocity times density. Okay, so this bit here is just to emphasize a single point that you cannot sort of take a pick between the above two examples that I gave you. In other words, how do we interpret vector fields? How do I think of them when I'm trying to relate to them physically? You cannot just decide I prefer to think of vector fields as representing forces, or for me it just makes more sense to think of them as representing flows of fluids. You can't just pick one. Both of these are going to be really important. There are some very, very important things that we're going to do in this course that will require you to think of a vector field as representing forces. And if you try to make sense out of it in terms of fluids, it's not going to make any sense at all. Right? So it's not optional. You've got to be able to understand. You've got to be able to interpret a vector field in some contexts as representing forces. But the thing is, there are some situations where it only makes sense if you think of it as a flow of a fluid. And again, so if you hang your hat on, I'm going to think of vector fields as always representing forces, then you're not going to be able to make any sense at all out of some of this other stuff that we're going to do. You really need to be able to think of them as fluids also. So I want to make a big deal out of this. Some students tend to sort of, I'm just going to do this one and let the other one kind of go. So make sure that you don't do that. It's a problem. Okay. So the book does what I think is a little bit of a weird thing here. The book introduces various operators. They're things that you can do to vector fields. Certain kinds of calculations that you can make on vector fields. And the book introduces a bunch of them here. And the reason I think this is weird is because they introduce these operators without any context, without any motivation at all of why would I ever be interested in such a thing? Right? Why would I write this down? Now, there are answers to those questions. And if it was up to me, I would like to introduce these operators as they arise naturally, in context at least, so that you can, when you see these operators, you see where they're coming from. The book wants to get them introduced, and then we'll justify them later. Anyway, it's not what I would have preferred to do, but it's, whatever. It's not my book. So that said, there are some exercises where you're going to have to do some computations with these operators, so I have to introduce them now. But I just want you to know, if you're wondering, for example, I don't feel like I have a good intuition for Green's operator. Well, yeah, of course. I know that. I think that's weird too. So you should not, at this point, have any idea why we would ever care about this expression. Is that cool? Right? So don't feel bad if you don't have any intuition for why we're doing this. That's very appropriate. Okay, so that said, a vector field. Keep in mind, a vector field is a function. It gives you, we associate to every input point, we associate an output vector. Let's go ahead and refine our notation a little bit in this context. Notice this output vector, each of the coordinates is defined by a formula, right? You can look back at vector fields that we've seen here. Well, let's just go back to, here's one. This output vector, right? There's formulas for the individual coordinates. The first coordinate of this field has a formula, negative y. The second coordinate of this vector field has a different formula. It's x in this case. Okay. All right, so I'm going to introduce a very standard notation here, which is to call those coordinates P and Q. All right. By the way, another very natural choice is to call them F1 and F2. That makes a lot of sense because they are the first and second coordinates of this F vector field. So you'll see that sometimes. But anyway, I'm going to go with the book's convention. We'll use P, Q. Very, very common choice. All right, and with that said, Green's operator is computed by this formula for reasons that will become clear later. Okay, so at the moment, you just need to know the formula. It's Green's operator. Memorize it. It'll be very useful later on. Okay. There's this other thing that you need to know. It's called the divergence of the vector field. It is computed with that formula. Context to come later. Right? As of the moment, it's just a formula to memorize. Apologies. Okay. Okay, notice these are for vector fields in R2, right? So there's two components there, and so R2. There are, of course, also vector fields in R3. If you have vector field in R3, here's the notation that we typically use, P, Q, and R. Right? Again, you'll also see F1, F2, F3, and that kind of thing. Here we're going to use PQR, just like the book does, very standard. Here are a couple objects that end up being interesting. This thing called the curl of the vector field is computed by that kind of weird formula. Again, context later. This thing called the divergence. Oh, there's that word again. It looks just like that divergence. The divergence of a vector field computed by that formula. Now you'll notice that this formula makes a pretty prominent appearance in the other formula, right? So that's, I'm going to say, ultimately not surprising once you understand what this is physically representing. But for the moment, it's just formulas. Just memorize. Don't worry. Just memorize for the moment. Okay, now there is another little notational bit that I want to introduce. This is very, very common notation. It's a very convenient notation. When I was as part of my second major in physics, when I was an undergrad, I saw the notation I'm about to show you down here. I saw this notation more than I saw these notations for divergence and curl. These, by the way, are pretty easy to relate to. That stands for divergence. Right? Nobody needs clarity on why that was the choice of notation there. So here's this other notation, though. It's very common. And that is, recall that when you write down the gradient of a function, the formula is partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z. And the idea is to say, well, it's like this thing here is the thing that you are doing to that function f. Right? What are we doing to this function f? Well, we're taking 3 partial derivatives and making a vector out of it. Well, okay, so the act of taking 3 partial derivatives and making a vector out of it is what we view that symbol as representing. Right? It's a notational sort of like choice. It's a notational choice to view the upside down delta, the triangle, that little symbol. They call it nabla for some reason. Sometimes, more often, people call it del. Just whatever. So that del operator is that thing, whatever that means. Right? The motivation, I think, is again pretty clear. Okay, I emphasize though, this thing here is not gradient. Right? Gradient is what you get when you take that del operator and then you apply it to a function. Then you get the gradient of that function. By itself, it's just the del operator. That's it. Okay. All right. So with that in mind, del being what it is, if you were to make some interpretation of, what should that mean? What should I get if I take del? Right, if I take, partial with respect to x, partial with respect to y, partial with respect to z, if I do that, and then say dot, a vector field, let's see, I'll use here, a vector field, P, Q, R. What should this mean? That is kind of, notational nonsense in a way. This isn't really a vector, right? The partial with respect to x is not a number, right? It's an operator. So that in mind, if you would interpret this in a reasonable way, how about this of that, that of that, this of that, right? Do the dot product, the way it would seem reasonable to do it, and notice you get exactly divergence. It's just, works out. How convenient, right? So they noticed this a long time ago, and it's extremely common, and it's beyond just notationally convenient. There's actually really good reasons. There's ideas, if you use this notation, there are certain ideas that end up working out really nicely. So anyway, you're going to see, with this in mind, you're going to see this notation to represent divergence as an alternative to that notation. For whatever reason, mathematicians tend to use div. Physicists tend to use del dot. I don't really know why. Okay. I can speculate, but let's not. So along those same lines, if you were to write down, del being this, and if you were to make some reasonable interpretation of what should that mean, right, it turns out, the only reasonable interpretation is you're going to get, in fact, exactly curl. So del cross, very common notation to represent curl, and it just is. All right? So heads up, be aware of that notation. You're going to probably see me using those notations a lot because, again, second major in physics, they made me do it a lot, so I kind of developed the habit. So del cross and del dot. Okay. All right. So last thing I want to talk about today, this is going to work out kind of perfectly on time, I think. I want to talk about some of the relationships between these. Again, this is all very premature. right? So I can't tell you yet what Green's operator represents. We're going to totally do that later. But right now, it's just this thing that you compute because the book says so, right? And likewise, what is curl? What is divergence? So it turns out that it makes sense, and we will make a lot of sense out of this. It makes sense to compose the gradient operator and Green's operator. Now let's think about that. I mean, the gradient operator, you take a function, you take its gradient, and what comes out is a vector field. Green's operator is something you compute on a vector field, and out comes a single coordinate, namely just a real valued function. So you can Lego those things together like this, right? And it fits. If you have a function, you can compute its gradient, and of that gradient, you can compute Green's operator. And like I say, for reasons that we'll talk about more later, a little bit in a few moments, it turns out this is a very sensible thing to want to do. Okay. Likewise, in R3, the Legos fit together slightly differently, but notice that gradient takes a function and gives you a vector field. Curl, look back at the formula on the previous page, takes a vector field, gives you another vector field. And divergence takes a vector field and gives you a function. Again, it turns out that it makes just great sense to compose them together like this. Okay, so the first thing I'm going to show you on why this makes sense is it turns out that this is what we call these are what we call exact sequences. So everything has a lifetime of 2 is the way I like to think about it. Yeah, question.
On the above sequence.
Yeah.
Is the original function the same as the function that comes out?
No. This is just. I mean, what goes into the gradient operator is something taken from the world of functions, and what comes out of divergence is something that is, from the world of functions. So I don't mean it's certainly not the same thing. Absolutely not. Yeah. Okay. So everything has a lifetime of 2, and the idea here is that if you have some function, if you compute its gradient, and then you compute the curl of that, you will get 0. That's weird. Right? Who saw that coming? Right? That's not obvious that this works. You can calculate it out and confirm that that's the case, but it's really not obvious. Right? Here's another version of this. Everything has a lifetime of 2. If you compose things in this way, another example. If you have some vector field whose divergence is 0, again, I like to think of 0 as representing, it's nothingness. It's kind of like death, if you will, dark metaphor. But if the divergence is 0, that means that vector field must be the curl of some other vector field. Because this cannot be the entire lifetime story of that object. It must have had a lifetime of 2. Here it is. Everything dies after 2 steps. And so it must have come from previously the curl of some other vector field. Anyway, that's pretty, that's an eyebrow raiser, right? It's strange that this lifetime of 2 thing always works. There are a couple of exceptions here. I don't want to get bogged down in these exceptions, but it has to be said. So anyway, making these, grouping these together like this, very natural in a lot of ways. I'll say more about that much later on. Anyway, heads up about that. And wow, we ended right on the second at 11:10. So great stopping point. See y'all on Friday.